Okay, so I said we're going to look at an example here of doing an integrator, and we are. We're going to look at a quick example here. So, whoops, I'd like to have it in black here. There we go. So let me draw the circuit here. It's going to take me a second. So, let's see here. The capacitor has no initial energy. How long does it take for the op amp to saturate? And then we're going to go to sketch, input, and output. So we'll sketch the input voltage, which is pretty boring because it's just a constant 4 volts, but we'll also sketch what the output voltage is. And we're going to do that just to really illustrate the fact that this is an integrating op amp. Now, I know we have this formula here that V out is equal to negative 1 over Ri CF. Actually, there's an error there. I put a double negative in there for some reason. Again, you guys aren't here to touch my negatives. You know, I need you here. But we have this formula here for the integrating op amp. I honestly don't remember that formula usually. What I do is I just go through and do the nodal analysis every single time. So that's what I'm going to do here. Is I'm just going to go ahead and do the nodal analysis. So we have 0 volts here, 0 volts there, and then I've got a current going up here, and then a current going to the right. And so the current going to the left, of course, that's just a simple Ohm's law. So we'd have 0 minus 4 volts over 12 kilo ohms plus, and then what would we have here? Well, we'd have, I'll call this IC, because it's the current going through the capacitor, equals 0. And so we'd have 0 minus 4 over 12 kilo ohms plus my capacitance, which is 500 nanofarads, times the derivative of the voltage. Now remember, it's the derivative with respect to t of, well, the voltage across the capacitor is 0 minus my output voltage. And then this is equal to 0. Now I'm still going to solve this like I would kind of any other thing here. I'm going to go ahead and multiply through by 12 kilo ohms. So if we do that, of course, on the left-hand side, we just have initially, whoops, keep forgetting to change my colors here sometimes. Negative 4, because the 12 just cancel. Now let me punch in my calculator real quickly what this would be. I get, and I'll go ahead and write it as 6 milli. Actually, instead of writing 6 milli, that might be confusing here. Let's just go ahead and write it as 0.006 times the derivative of minus V out equals 0. So now I just have to solve this. So again, what I'd have here is 0.006 derivative of my output voltage is equal to -4. And then we get that the integrating both, well, first what we'd have here is derivative with respect to t of the output voltage. And I'm going to go ahead and write this as a fraction. It gets you -2000 over 3, which is, of course, -666.6666. So we'll say -2000 over 3, just to keep some things accurate right now. And then we just solve this. Now, this is where we have to be a little bit careful. This is going back to Calc 2 or introductory differential equations. But really, this is Calc 2 because we're doing an indefinite or an indefinite integral here. So I'm going to integrate both sides. Or you could look at this as a separable differential equation. I mean, however you want to look at this. So we wind up on the left-hand side with V out. And then, of course, if you integrate a number, you get -2000 over 3t. But then remember, when you do an indefinite integral, you get plus constant c. And actually, I'm not going to do that. I'm going to call my constant k. And you should all know, if you're watching this video, why I changed that to a constant k, because c we use for capacitance, and we don't want to get things mixed up here. But I still haven't found a formula for V out. I still have to figure out what this is. We still need to figure out K. Well, that's where I'm going to scroll back up here. What did it tell me here? The capacitor has no initial energy. So what does that tell us again? This tells me that V at 0, I've got a second here, I've got a hair on my tablet screen there. V at 0 is equal to 0 volts. So we can use that to figure out what the constant K is. So we have 0 is equal to -2000 over 3 times 0 plus K, which of course gives me that K is equal to 0. Now you're not always going to get the constant being 0. You have to absolutely make sure that you substitute in to figure what it is. So then we get negative. So my final equation is that V out is -2000 over 3 T. So that's what my output voltage is. Now, the question here says, how long does it take for the op amp to saturate? Well, we have positive and negative voltage supplies here. And based off the equation, I'm getting a negative voltage out with respect to time. And I know the largest in magnitude I can get is -10 volts. And so what do we do here then? Well, we just set -10 is equal to -2000 over 3 times t, and we solve for t. And if we solve for t, I'm doing it in my calculator right now, you get 15 milliseconds for this op amp to saturate. So it saturates very fast, and you might say, well, why would we ever possibly want to integrate something that saturates 15 milliseconds? Well, we're talking about just DC voltages that we're applying. We're often going to be applying signals that aren't necessarily going to be just a constant. So sometimes we want them to respond really quickly when we're doing the integration so that we can actually integrate the signal appropriately. Now, the last thing this question asked was for us to graph it. Now, the graph here is pretty straightforward. I'm going to actually graph them on the same graph here. Okay, so let's just go ahead and label some things here. 2, 4, 6, 8, 10. Actually, these should be negative 10s here. So I'll do 2 graphs. Here, let me just shorten this one down a little bit. I didn't need this one as tall. So this will be my Vn. And it's just a constant 4 volts. And then let's look at what V out does. And I did it again. V out is actually going to be negative because it's negative 2000 over 3. And so V out is going to look like this. And then that time where it saturates is what we found was 15 milliseconds. And now again, see how when we integrate, we're getting, if you integrate a horizontal line, you're going to get a straight line. And if we were to throw this through another integrator, you might guess what we could get. We'd get a parabola shape. And you actually would get that. So it's kind of interesting, and it's actually interesting because it also provides you ways of creating different types of waveforms, as opposed to just always having to do DC things. There's other ways to create waveforms as well, but this is one way you could do it. Alright. One last thing I want to talk about in this video here is I want to talk about this circuit here. And I'm not going to put the power supplies on this either. Now, I'm going to look at the circuit. I'm going to scroll back up, so hold your eyes here. Alright, so I'm going to scroll all the way back up to the top. If I look at this circuit, actually what I would do here is, let's see if I can do this here. I'm going to pause the video for, actually I think I can do it right here. I'm going to lasso this, see if this works. Copy it. And paste it. Oh, look at that. Using technology while I'm making a video. Okay, so let's look at this circuit here and compare these two. We just know from our discussion that we called this circuit an integrator, because what did it do? It integrated. Now, if we look at the difference between these two circuits, there really should only be one difference that we see here. And hopefully you can see the only difference is that we flipped the location of the resistor and the capacitor. So if you had to take a guess, at least if I had to take a guess, I would guess that this would actually do the exact opposite of integrating. I would say, well, this is probably going to do a differentiation. or differentiation. Well, let's show that that's indeed what we get here by doing circuit analysis. So again, let's just start off here. I've got 0 volts. That means this point here is 0 volts because of ideal op amp. I've got some current coming up here, current going to the left, and I'll just call those currents I1 and I2. So we have I1 plus I2 is equal to 0. And then I1 is the current through the capacitor now, so this is going to be the input capacitance times the derivative of the voltage across the capacitor. But remember, the voltage across the capacitor would be the voltage at this point minus the voltage here. So it'd be 0 minus Vs plus, then using Ohm's law, we'd get that the I2 current would be 0 minus V out over RF equals 0. Now let's go ahead and do some manipulations here. We get Ci times the derivative of negative Vs minus V out over RF equals 0. And then doing a little bit of solving, remember what we want to solve for. We want to solve for V out. So V out over RF is going to be negative Ci times the derivative of Vs. So V out is negative RF Ci times the derivative of Vs. So this right here is my final equation that I get. And look, what am I doing? My output voltage is the derivative of my input voltage. Now, it doesn't make sense really in some cases here to talk about that, because if you have a constant voltage in here, like 4 volts, if you have just a constant 4, what's the derivative of a constant? It's 0. So you'd be like, well, that's not doing much for me. And no, it's really not doing much. But we will actually use this differentiation type of thing here to create something that is useful for us. And again, if you're having other signals, like if you had a sawtooth waveform, for instance, if this was what Vs looked like, or actually, instead of a sawtooth, let's do a triangle wave. So a triangle wave. So suppose Vs looked like this waveform. Suppose it looked like this. Then the derivative of Vs, and I know there's a negative and everything else like that, but I'm not really concerned about too much about that. The derivative, well, these are just straight lines, so the derivative would give me something that looks like this. And in fact, what we're going to talk about on Friday is basically how can I create this, then get this, and then we're going to do PWM. We probably won't get through it all on Friday. If you have questions, make sure to email them to me, and we will also take time on Friday to go through questions.